All right, folks, you need a notebook, your reference table, your pencil, and your calculator. Today we will start Unit 5, which deals with projectile motion. You had a reading assignment for today. Hopefully you did it because I'm going to go fairly quick through the presentation, assuming that you did the reading that I asked you to do for today. For Wednesday in your Unit 5 packet, you need to answer questions 1 through 17 on pages 9 through 13. Okay, so that is right after the reading assignment that you did for today. Those are all multiple choice questions. So make a note of that somewhere, that for Wednesday of this week, you're going to want to answer questions 1 through 17 on pages 9 through 13 in your Unit 5 packet. They're all multiple choice, all conceptual. Okay? They're all multiple choice and all conceptual questions. There's no math involved with the assignment that is due Wednesday. It's not due tomorrow because, of course, there's no school tomorrow for the federal holiday for Veterans Day. I'm also reminding you that if you have your Unit 4 test corrections or are eligible to do that, that those would go in the blue bin on your way out of class or during the break. Those are due Friday. Please make sure you get a signature on them. I really don't like not giving you credit for doing the work, but if you don't get the signature on there, I'm not going to give you the credit. You have to have that. All right. Any questions for me before we start Unit 5?
When do you get our board?
You'll get it back once everyone has taken it, which will be a few days because it's not just me, it's all the physics teachers that gave it. So we have to make sure all the students in the department have taken it. Hopefully Wednesday, because the quarter ends. We all have to get our grades in 8 a.m. on Wednesday. So if it's not done, it's not made up today, it goes in as a 0. And then whatever. Okay, so let's get started with Unit 5, Section A. And as I mentioned, this unit is about projectile motion. I did ask you to number all the pages in your packet and to write Unit 5 packet on top. So hopefully you did that, because otherwise, when I refer to page numbers, you're going to be like, where's that page? All right, so hopefully you did that. So we're going to be continuing our study of kinematics. This is our last unit of kinematics. And it's about the study of projectile motion. And what we're going to do this first class period is to understand just some basic characteristics that all projectiles have. What characteristics do projectiles have? And this is what your assignment is on for Wednesday. I'll ask you to define the following terms, including projectile, trajectory, and range. You'll need to know what is meant by those terms. You'll need to be able to describe the shape of the trajectory of a projectile and explain what causes that particular shape, which happens to be a parabola, and then break down the components of the projectile's motion into horizontal and vertical, or X and Y components. So there's a little bit of trig involved with that. All right, so let's get started with our first vocabulary term, which is the term projectile. What do we mean by a projectile? A projectile is any launched object. So you are launching something. You're launching it. And once it's been launched, the only thing that influences how that projectile will move is gravity. We're going to continue with the assumption that there is no air resistance to deal with. Specifically because we don't have the mathematics that we need to be able to solve problems with air resistance in the Regents course. So what this means is that everything we studied in Unit 4 is a projectile. But we simplified our understanding of projectiles with just things going up and down or straight down. Now we're going to be dealing with things that not only go straight down or straight up and down, but they're going to go outwards while they also go up and down. So we're looking at anything that is moving under the sole influence of gravity. That's what a projectile is. Anything that's moving under the sole influence of gravity would be a projectile. Okay, may I go on? So that's our first vocabulary term, projectile. There are basically three types of projectiles that we will talk about. The first one is the one that we did in Unit 4A with an object that's dropped. So Unit 4A, even though that was Unit 4, we are still going to be referring to that type of motion with an object that just drops down to the ground. Then 4B was about an object that we threw straight up and came straight back down on itself. That was 4B, the object that's thrown straight up. That's still testable in this unit because it's a projectile. This is the type that we're going to focus on, though. Things that go up and down while they are moving outwards. Objects that are given some type of velocity at an angle, so they not only go up and down, they also go outward. And you can see the kind of path that we get there. Let's talk about that path that you see, the ticker tape that's drawn there for that third type of projectile. That's called a trajectory. A trajectory is the path of the projectile. It's the path of a projectile. That's what we mean by trajectory. What we will see in this unit, what our focus will be on, are projectiles that are moving horizontally, meaning outward, forward, while they are also moving up or up and down, or down, out and down. And when we look at that trajectory, this is what we see there. That path is always going to be a parabola. It's always a parabola. We'll talk about what creates that parabola in just a minute. So that gets us through two of the three vocabulary terms that we need to be aware of. The first was trajectory. The next was projectile. And the third and final new vocabulary term is the term range. And what the range refers to is how far out a projectile will move. And that is from its launch position here to its landing position here in the horizontal direction exclusively. So range refers to how far out something moves. It is not measured from our starting to our end position. It is always measured sideways, horizontally, from start to end positions in the X direction exclusively. Okay, may I go on? All right, so let's do a little thought experiment, and you'll understand why we can't do this experiment in real life in just a minute. I want you to imagine that we are going to shoot a cannonball out of a cannon whose barrel is horizontal, and we are going to launch it off the top of a very high cliff at some really high speed. Here's where we have to do the imagining. Imagine that somehow or other we could turn gravity off there. Okay, so there is no gravity that exists there. My question to you is this. What is the motion of the cannonball going to look like? How would you describe what the cannonball does once it's launched?
It'll travel in a straight line horizontally.
Yes. And can you describe its velocity as it travels horizontally in a straight line? Yeah, it would be constant. So let's make a little sketch illustrating what happens when there's no gravity to consider. So let's say here is our cliff. That's really high. And what we're going to do here is we're going to take our cannonball and we're going to launch it horizontally. As Nikolai said, if there is no gravity, it's going to continue at a constant velocity in a straight line. So if I were to draw a ticker tape, where would we see the cannon? What would the ticker tape look like for that cannonball? What does a ticker tape look like for anything that's traveling with a constant velocity? Yep, that's right, equally spaced. So let's go ahead and draw that. The cannonball would be at equal distances in equal amounts of time. And it would continue like that forever. It would never come down to the ground. Why wouldn't it come down to the ground? Because there's no gravity. This, I'm going to add my velocity arrows. All these velocity arrows would have to be exactly the same because we'd have a constant velocity. This is what we call our gravity-free path, where this velocity, which happens to be horizontal, so because it's horizontal, we call it v sub x. X is a horizontal direction. It's constant. So those dots would have to be equidistant. Okay? Make sense so far? I'm trying to build to something. All right, so let me now go back to this thought experiment. We just said it's going to continue in a straight line at a constant speed because without gravity, there's nothing that would pull it down to the ground. You can see that those dots are equidistant. That is our gravity-free path. Now let's try this thought experiment again. But this time what we're going to do is now flip the switch and turn gravity back on. Turn gravity back on. I want to know, when I turn gravity on, what effect gravity has on the motion of that cannonball. Is gravity going to affect how it goes out? Does the cannonball travel greater or shorter horizontal distances every second because of gravity? Does gravity pull you sideways? Okay. So would it ever affect your horizontal motion? Okay, let's do a little experiment here. Let's kind of draw what happens. If we turn gravity on, let's forget that it's going sideways. I just have a cannonball here and I'm going to drop it. And gravity is on. What is the ticker tape going to look like for that cannonball when I don't launch it sideways, I just drop it? What's that ticker tape going to look like, Ryder? Yes, further and further and further apart. So it would look something like this. And so on and so forth. Actually, let me even exaggerate this a little more. Like that. This is the dropped path. That has gravity. What happens when you launch something sideways and gravity is acting on it? It does both of these things simultaneously, which means that the cannonball after 1 second is not here, nor is it here. It's in both of those positions simultaneously. So let's superimpose those. It means the cannonball is actually there. Instead of it being here 2 seconds after it's dropped, because we launched it sideways, it's not just here, it's at both of these positions together. Right there. Instead of it being here 3 seconds after it's dropped, or 3 seconds without gravity, it's going to be in both of these positions at the same time, right there. Instead of it being here or here, hello, Mr. Bowman. Yeah. We're going to combine those motions, and it would be here. It's doing both of those things at exactly the same time, which results in this parabolic shaped trajectory. This is what we see. But where it comes from is the outward gravity free path with the dropped path. Those things happen together. We can't see this. We can't see that. All we see is this. But when we solve problems involving projectiles that are doing both things at the same time, we have to break it apart, because in one direction there is no acceleration, and in the other direction there is an acceleration. It's accelerating downward at 9.81 meter per second squared. So we see it accelerate down, but not out simultaneously. And that's how we have to really think about these types of projectiles, moving out and down together. Okay, do we all have that? And I think you saw this in the reading. You should have seen these pictures in the reading. So that should not look unfamiliar to you. Okay, so let's continue. As we just said, gravity is going to pull things down, but not out. Gravity is accelerating objects down, but it can't pull you sideways. Therefore, because gravity can't pull you sideways, it will never affect how you move outward. It can only affect how you come down to the ground, the vertical component of motion. So here we can see that gravity-free path. Here we can see the dropped path. Remember, it's going to do both of these things simultaneously, which results in our observation of the parabolic shaped trajectory. So with gravity, as we said, we get that parabola. Gravity is pulling things down to affect the vertical component of motion. And that's where we see the acceleration in the vertical direction, causing things to fall directly below their gravity-free path. Okay, can I go on? I'm not seeing any no's, so I'm going on. All right, so let's just review some of the characteristics of these projectiles that we're going to see. As we just described, the motion of the projectiles that we are predominantly going to focus on in this unit will occur in two separate directions simultaneously. Things are going to move horizontally in the X direction while they are also moving vertically in the y direction, up and down. Because the horizontal and vertical motions are perpendicular to each other, right? X and Y are always perpendicular when you draw the axes. It means that the two motions are independent of each other. One cannot affect the other because they are perpendicular. Right, can I go on to the next slide? Okay. So as I just said, because they are perpendicular, they cannot influence each other. They are independent of each other. That happens anytime there are multiple directions of motion which are perpendicular. It's not just with projectiles. This happens anytime there are two different things occurring simultaneously. Because they are independent of each other, we have to treat the X and Y directions completely separately, as if the other direction of motion does not occur at all. So what this means is that what we observe, the parabola, we are never going to work with that. You're going to have to break that down and kind of go backwards from what we did. Remember that what we did was we started with our gravity-free path and the dropped path, and we combined them to get the parabola. Now what we're going to be given is just the parabola. And then you have to break it up into this and this. You're going to go backwards. Instead of me giving you the two separate motions, you're going to be given the combined motion, and it be expected to break it up into those two separate parts. What's going on outward with what's happening vertically. Giving you that parabola. And then depending on what you're asked about, you're going to have to forget that the other part of the motion exists. Just kind of ignore it. So if I ask you about it going out, ignore the fact that it's coming down to the ground. That's the gravity-free path. If I ask you something about it coming down, you ignore the fact that it's going out. So let's see if we can kind of describe, therefore, what's happening in each direction separately. Remember, in the X direction, that's where we will see that there is a constant velocity. The horizontal motion would be described as having a constant velocity. In other words, there is no acceleration in that direction. Right? And we already described that on our picture, that's where we have our constant velocity and no acceleration. That is our gravity-free path. Let's talk about what's happening again in the Y direction, the vertical direction of motion. This is where we have gravity. The Y direction is under the influence of gravity, and the acceleration we have in the vertical direction, remember, for Earth is negative 9.81 meters per second squared. And that's what creates that type of ticker tape for something that's dropped. Okay, we're going to do one more thought experiment. You ready? It's described here on the left. This is a question that is asked about all the time. It says it's a famous physics question. Ringo is this dude on the left, and let's imagine that's me on the right with my large bazooka. Now, Ringo has a bullet here in his hand, and I have a bullet loaded in the barrel of my bazooka. And I want to know if Ringo drops his bullet at the same exact moment that I shoot the bullet out of the bazooka, which one hits the ground first? And notice that both bullet and the bazooka are at the same height off the ground? Okay, do you have an idea? I would like you to go ahead and write your hypothesis in your notebook. You can write hypothesis. This is what we call the dropped versus fired bullet experiment. Which one hits the ground first, assuming they are starting off at the same initial height? One is dropped, one is going to be fired horizontally. Which one is going to get to the ground first? I could think of 4 possible answers. The bullet gets there first. That Ringo drops. Second possible answer, the one fired out of the bazooka gets there first. Third possible answer, they both get there at the same time. Fourth possible answer, neither one ever gets to the ground. You have your hypothesis? Okay. This is what we would be witnessing. I'm showing you a simulation here of a bullet that's dropped in red and a bullet that's fired horizontally in blue. Remember that. Just focus on those two. Ignore the green ball on the simulation. The one that's fired horizontally is going to move in a parabolic shape. It has horizontal and vertical motion. The one that's dropped just has the vertical part. But what brings it down to the ground? Gravity. Is gravity the same for both bullets? Yeah, because it's on Earth. As long as you don't change the planet, they will both experience the same vertical motion. So when you look at those two, the blue and the red, ignore the green. Here we go. You see how they fall together to the ground? How many of you predicted they would land at the same time? Very good. You can see that there in the simulation that they move down to the ground together. The horizontal motion is that gravity-free path shown with the green dot. What we do is we combine them together, and they both land at the same time. So hopefully that is what you predicted. I think that was also described in the reading as well, so you're testing yourself there. They will both land at the same time because what pulls them down to the ground is exactly the same. They are going to travel the same vertical distance. They have the same acceleration from gravity, which means that they both land at the same time without the effects of air resistance. All right, now we can demonstrate this. How many of you have heard of the show Mythbusters before? Okay, Mythbusters actually did that experiment in their lab. So let me show you the video clip where they did this.
Everything's hot. Let's do it. And after a few test fires and a bit of fine tuning, it works. Oh, it's good. It's good. It's 1/3 of a millisecond difference. Wow. That's freaking perfect. Let's go do this full scale.
Okay.
Which means rolling up the room 360 feet to stake out a drop zone.
Right about there. That's where they were landing out in the shooting range. So this is where I expect them to land here.
Okay.
Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history.
All right, dude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet dropped versus fired. In 3, 2, 1.
360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. Oh, I can't wait to see the high speed. So, dude, this bullet carved a streak right under the drop zone. I think this might be the shot we've been looking for.
In real time, it's impossible to tell what happened. Until Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves. And a victory for physics.
All right, so did you hear there was a slight difference? How much was the difference? 39.6 milliseconds. Now, what was the why do you think there's that difference? They said initially that there was a difference. I think it was a third of a millisecond. They talked about at the beginning of the video, getting the electronics to fire it exactly, to drop and fire at exactly the same time. It was a third of a millisecond off. Why do you think there was a 39.6 millisecond difference at the end? Not because of the technology. The technology gave it a third of a millisecond difference. There's a much more obvious answer. Air resistance. There was air resistance in there. And you get more air resistance the faster things are moving. Which one was moving faster? The dropped bullet or the one that's fired out of the gun? The one that's fired out of the gun. So that's why we see the one coming out of the gun hitting a little bit later. It's hitting that paper a little bit later, 39.6 milliseconds later, because of the effect of air resistance. They couldn't get the air out of that room in order to do the experiment. But again, it is so small that we essentially just ignore it for the purposes of what we're doing today. Okay? Questions on what we just learned? Okay. So what I'm going to do now, we have a little bit of time left this period. We have about 8 minutes. So what I'd like to do is give you the 8 minutes that we have now to start working on the assignment in your packet. Next period, we're going to start section B. Next period, we'll start section B. So go ahead and take out your packet. Turn to page 9. Remember, if you did not number all your page numbers in your packet, please do so now. If you number them correctly, you will get to page 40. Okay, if you number them correctly, you'll get to page 40. And you can start working on those 17 multiple choice questions now, which are due Wednesday.